So that's why we say, we are made from stardust, because we are here and everything is in the space. So if we are made from the stardust, then other life form should be made from stardust too.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff, with departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others. The college always has something exciting happening. Join us to find out what's new now.
Joining me in the ASC Marketing and Communications studio is Sultana Nahar, research professor in the Department of Astronomy at The Ohio State University. She is the winner this year of the William Fowler Award for Outstanding Research in Atomic Astrophysics from the American Physical Society. Dr. Nahar, welcome to Voices.
Thank you.
And congratulations on your award. Perhaps we should start there. For what research did you win this award?
Okay, it's largely accumulated research. It's not a particular one. So I've been doing this kind of atomic astrophysics. You can say I'm one of the co-founders. It's one area of astronomy or physics together. And so my accumulated work is on atomic processes in astrophysical plasmas and applications. And all those things are accumulated in two forms. One is a very unique atomic database. It's called NORAD Atomic Data. It is based in the astronomy department. It is unique because it has many processes and very accurate. It has data for about 250 atomic species, and a lot of users, largely astronomers, but also physicists and engineers, chemists, they all come to this database to download the results. So there has been a metric to see how many users come for the last 1.5 years, and it's close to, I think, 300,000 users came. But last month, I think there was the largest number of people access the data. It was in 1 month, I think it's 28,460 or something, the 65. Yeah, so this is an atomic database and it's all my results. So that's why it is unique and it is very accurate. It covers a number of areas of atomic processes. The other one is also the book that I have written with the Professor Anil Pradhan. It is called Atomic Astrophysics and Spectroscopy. It's the bridge between physics and astronomy. There are many things of physics that astronomers don't understand, and also there are many things about astronomy that physicists don't know their application to it. So this is the book which bridges these two areas. So it has been a very popular book all over the world. Actually, you can go any country. It is published by Cambridge University Press, and we are actually working on the new edition because there have been some more developments.
Well, you said that there are some things that physicists don't know about astronomy, some things astronomers don't know about physics. Give us some examples of what that might be.
Okay. For example, astronomer is using the spectrum. The photons, they come from the stars or astronomical objects. We analyze the photon to understand on what is at that astronomical object. Not only that, the line also gives information, the condition, like physical condition, or what's the temperature of the plasma, density of the plasma, what kind of environment. So all we can extract just from studying the photon coming out from the atomic species in that an astronomical object. So what they do, they take the numbers, parameters related to that process, but they don't understand the underlying science, which is giving that number. They're just using the model, for example, for applications. They don't understand what is more accurate, why this is say, more important than the other one, that physics part. And physicists, they are so much involved in studying a particular phenomena of the atomic species. They don't know that it is applicable to astronomy Okay, they're studying a lot of things, but if there's, it's like an island of knowledge. If you connect, then, it becomes richer, you get more connection, more applications. So astronomers, for example, I'm studying this kind of atomic species and studying light interaction, but I don't know, this has some application in particular kind of objects, like in black holes or in nebular object, where just the plasma, or in a star or in a supernovae, that kind of thing. So it is, they just know that I have to use this parameter, and they keep on working, but they are not connected. So this one connects, tells this is the astronomy and this is the science behind it, underlying science. Yeah.
This surprises me, I must say. I didn't realize that there weren't that many bridges between physics and astronomy.
Oh, they are actually, astronomy is based on all areas of physics. So they are actually very much related, but you suddenly become so much focused, only whatever you're seeing from space, outside, anything outside our Earth, is like in astronomy. So you're becoming anything coming out from there that you don't relate, the things going behind it. And all kinds of physics are needed to study astronomical objects. And only things that we don't bring the astronomical objects to our laboratory. So what we do, we just study one thing, the radiation coming out or the signal we catch. So from those things, signal or the radiation, we get a lot of information. We can predict a lot of things. Even can say that planet has a life form or not, or is it a black hole, or what is going on? Is a new star or old star, or it is the beginning or the end. All those information. Okay?
Well, I'm interested in diving more into that, but before we do that, you've made mention a few times of plasmas, and I wonder if you could tell us what plasma refers to.
Plasma is like we know solid, like table is solid, air, so it's just the molecules are there. Plasma is something, another state. It is, you can say, not pure gaseous, because you have atoms there which are charged. Like when we say an atom, charge means the atoms have lost some of their electrons, maybe one electron or two electrons. So if we have it, like a lot of atoms in gaseous form, but they are not neutral, that means not all the protons are neutralized by the number of electrons. So we knock out electrons, which are easy to knock out. We call it plasma. And plasma state, the 99% of the matter in the universe is in plasma form. All the stars are plasmas.
So it's a state of matter.
Yes.
When I was a student, there were only 3 states of matter, right? Solid,
Yes.
liquid,
and
gas.
gas.
So what happened, and especially if plasma makes up so much of the universe, how has it only, recently become identified as a state of matter?
No, it has been there a long time. Plasma,
Well, I'm an old man now, so...
The reason it is different because the characteristics are different. You want to study plasma, it has different kind of characteristics. You want to use gas, just pure gas, they have different kind of equations to represent or express them or describe them. But plasma needs its own set of descriptions, so it is a different state. And plasma, why? Because, the universe is made of largely water. The stars, we know, right? Well, we are not talking about dark matter, dark energy. Only 3% of the whole mass we know is in matter. Matter means, which we know, like in the periodic table, hydrogen going up to, 108 atomic number element. So all of them are in plasma state. In the stars, actually the way the stars form, like, the atoms are just drifting. Then they find another atom here. So gravity slowly pulls it, and other atoms or ions are coming. Ion means when you knock out the electron. So slowly you accumulate large amount of matter, and so it is forming, galaxy or something forming. Then the gravity becomes very strong, because you have a lot of matter. Then there is a sudden collapse. when you have this collapse, then there's so much pressure and temperature that becomes a perfect place for nuclear fusion. Okay, and so they form together and form stars around it. Okay, the new stars start to born, you can say. We just say born because they have lifetimes, so they die also. They're born, they live through a life, and they die.
I know that one of the things that you're doing in your research is, do I have this right? Are you looking for extraterrestrial life in the universe?
Oh, yes, of course.
You have to tell me more about this.
Okay. See, we cannot be the only one living on the Earth. So we have been looking for life form for a very, very long time. The SETI set up, a search for extraterrestrial life, that in collaboration with Soviet Union that time and US at this project. There are a lot of data, but we don't have concrete evidence there's a life from outside. It has to be, the signal. The signal can be pattern, particular kind of things that you can extract information. It can be noise. You don't want the noise because they don't have particular characteristics or properties that you can extract information. So since we are discovering a lot of exoplanets, so far we have close to 6,000 exoplanets, definite that we know. So these exoplanets belong to various stars. So if we are also planet of the star, our star is the sun, so those planets belonging to various stars, they can also have some kind of environment where living form can survive. Now, why we think about like ourselves? We are made of largely water, right? And other elements like calcium, iron, other things. All these elements are scattered in this space. So that's why we say, we are made from stardust, because we are here and everything is in the space. So if we are made from the stardust, then other life form should be made from stardust too. May not look like us, maybe different way, different form, depending on the environment, but there could be life form like us. So we've been searching for life form, and we think there could be, a lot of intelligent ones. Okay. Now, life form, what are the signs that are life form? So we know that if it is DNA or RNA based, which are the main ones? We know carbon, nitrogen, oxygen, water and hydrogen, they are there, right? So there, but we have extra ones, right? We call all of them like biogenic element or molecules. And among them, in the DNA, there is one element which is phosphorus. It is there. And it is very much active. It helps in communicating, to cells in the body. Strangely, we don't find phosphorus in this space. So that's why it was to say, is it the missing link that we don't find any life form outside because we don't find much phosphorus, and we are abundant, we have abundant phosphorus in the solar system. Why not outside? Actually, so the reason is not that it is not there probably, because phosphorus is very active. Active element means, it combines with others. And then it's very difficult to detect. Maybe it is there, we are not able to detect. So now with more sophisticated instruments in the observatories, like space telescopes are usually called observatories. So with those, we are detecting more phosphorus, more than before. So we have hope that we'll be detecting a lot more. Maybe we'll be detecting some phosphorus in exoplanets. If there's some life form in the exoplanet, when dye or something, our molecules on the body and limbs, they slowly float up in the uppermost layer of the atmosphere. And if it is uppermost layer, then we have observatories to take picture, collect photons of the exoplanets, by atmosphere. So they'll detect the elements, floating in that atmosphere. And if we find phosphorus, we can say that almost definitely probably the life form on that planet. So, but phosphorus is one thing, is so active elements, as I said, it combines with other elements. It has not been studied much. So what I'm doing, I have a project, we call it Phosphorus Project, kind of. It is for exoplanetary research. So studying phosphorus a lot so that when you see something, we have to identify that it is phosphorus. How do I identify? that's where it comes, underlying science comes to tell you that is phosphorus. So this is what I'm studying for exoplanet research.
Say a little more about that. What are the techniques by which you can identify phosphorus?
Okay, the technique is called spectroscopy. So spectroscopy means all elements, when they get excited. When we say excite, that means it got some energy. The electron has gone to an upper level. When it goes to upper level, it needs energy to go up. And when it drops down, it gives out that energy. And that energy comes out as a form of a photon. That's the unit of light. Mm-hmm. And that photon starts to travel, and our telescopes, collects those photons. And then photons, okay, is it a phosphorus photon or it is an iron photon? How do we know that? So that's why we have to study beforehand, because all these photons are unique to each element, each atomic species. So sometimes they have common lines, then we have to do a little bit more digging. Is it actually phosphorus or it is iron, if they have common line. All this space telescope on the ground and space, so what the purpose is to collect photons. Then we look at the photon and try to find out if this photon came from phosphorus or which element. And now we have our study already. We match. We do study, theoretical study, we do experiment. So the theoretical experiment and experiment, they also have to agree with each other. Then we establish, we have chart, tables of numbers. Then we compare. So this compare is one thing, okay? I'm just saying in simple language. But that photon can be, there's something called redshift. Have you heard about that?
I have, yes. Tell us a little more.
Yes. I will say, so when an object is moving, the photon is coming out. The photon stretches. Mm-hmm. So when it stretches, we call redshift. When it is compressed, like a photon is traveling toward me, is compressed. We say blue shift.
Blue shift.
Okay, the universe has been expanding. So most of the photons are also stretching. So redshift, James Webb Space Telescope, JWST, this is what it is doing, trying to collect the weakest kind of photon, because the more it is stretched, the photon becomes weaker. The energy is less. So on the side, I just want to make one comment. Do you know we have collected photons which have traveled from origin of the astronomical object for 13.1 billion years before it was caught by JWST. Isn't it surprising? A photon has been traveling for so long in the space. Most of the time the photons get, when they touch into something or interact with the atom, is gone. But some photons have been traveling and they become so weak. The reason JWST can catch, because it has very sensitive gold-plated, surface and a camera. Not only that, it is away, the furthest away from the sun. So solar photons, the light from the photon cannot disturb that telescope. So we are hoping that JWST will be able to detect probably some photons indicating life form outside our Earth.
So you mentioned, and it is extraordinary, the 13 billion years. It's just absolutely extraordinary. You've been talking about spectroscopy, and I'm really interested in some work that you've been doing with the spectroscopy of black holes from medical applications. You have to tell me more about this research.
Okay. The black holes, how do you detect black holes? You know that the black holes absorb everything, or not only matter, in lights also. So how do you detect? If I want to see this one, the light from this surface has to reach my eye to see it. I can see that writing because the light is coming to me. Okay. If the light doesn't reach me, then I cannot see it. So if the black hole does not give out any light, how can we tell that the black hole is there? It's from the environment surrounding it. The
things you can see around it.
Yes. So the surrounding tells us there's a black hole inside. The black hole is so strong, the molecules there, they're moving in so fast, they are ripped off all the electrons. And ripped off, they have just the electrons which is the lowest level. And when they get excited, they are giving out high energy X-rays. So these X-rays, from the X-rays and the surrounding X-ray, we can say that these X-rays can be emitted only if something, like black hole is causing it. So that's how we can detect black hole. But in medical facilities, how do you treat cancer patient? X-rays. Maybe it's different energy, but the connection is X-ray. So we are studying spectroscopy of black holes. Okay, so like I'm studying iron is one of the signature element for black hole identification. Okay, because around the black hole we have found iron. We call highly charged ion. Highly charged means it has 26 electrons, say, and it is moving so fast that outer electrons have more velocity than the other ones probably. So it is stretching, the whole thing is stretching. So electrons are ripped off. So it's left with not only 26, maybe 2 electrons only at the inner, close to the nucleus. So when, this energy around, excite, it gives out X-ray. So I'm studying this. Now, same study, same characteristics, I'm using it for medical purposes. People, would use medical X-ray. What they do, you want to treat a patient, they give some kind of liquid. It's called radiosensitizing agent. Then a patient drinks, for example, goes inside the body, and then they, radiate the person, with X-ray. The X-ray goes inside the body of the say patient is lying down, and you have that, fluid inside, for example. So this is one thing I'm just explaining. It breaks down that, and X-ray comes out, and that from that X-ray, you take image, and then from that image we can say, oh, there's a cancer or something, or sometimes we say X-ray to kill the malignant cell, but we sending X-ray. So what they're trying to do, the radiation oncology group at University of Rochester, they're studying that how can we create more X-rays to kill more cells. And there's one person who used to be in our group, a physicist, but he changed his area to radiation oncology. But because of physics background, he knows there are ways, the same element will give out more X-rays at certain energies. So they approached us. So Anil Pradhan and myself, we calculated and found out which energy, and what kind of element, if we shine, that will give out more X-rays. The way we're doing it is called spectroscopy. Spectroscopy identifies, which energy. So more plasma, that means, because of the electron breakdown, it creates plasma. So you form a nanoplasma, and that plasma will be absorbed by the surrounding malignant cell, and they die. If they absorb, that means it's dead. So then we actually proposed a new method we call RNPT. It is called resonant nanoplasma theranostics. So resonant means at a particular energy which will increase the amount of electrons. Nanoplasma, that means it creates plasma, a small amount of plasma. Theranostics means therapy plus diagnostics. So the X-ray, we can find out what is going on, and also we can do therapy, killing the cells. So this one got a lot of attention when we did that. And even, there's a magazine published one article called What Astronomy Has Done for You Lately. And it lists 4 items. It seems we are studying space, but so much application in daily life. So one is GPS. How GPS was created? GPS gives the direction. When you're in space, you don't know north, south, right? East, west.
What's up or down?
Yes. So, but you are focusing that your object should go, rocket should go there. So GPS is the one giving a direction. It was actually invented because of astronomy study. Number 2, so like for JWST, they had to do very precise, laser cutting. And that technology was picked up by medical facilities to do eye surgery. So that you can do precise eye surgery without much bleeding. So that's another application. And then was Wi-Fi. Wi-Fi came because of astronomy. So we are studying signals at NASA. It was an accidental discovery. They found out we can detect things without an actual cable connection. So it came from astronomy study. And the 4th one was our invention that we can use astronomy, studying the black holes, to cure cancer.
At what stage or why did you become interested in astronomy? As a small girl, did you know that you were going to study stars, or was this something that came later?
It came much later.
Really?
I was aiming to be a physician, doctor. I was interested in healing people because suffering is painful to watch. And my parents encouraged that very much. So then in the 9th grade, I came to physics. And physics seemed different. What is this physics? Studying abstract stuff. But I liked it. With physics, you can describe so many things with physics. I can describe you even. You are sitting there, yes, because the wave function which is describing you is very much a high probability around you. That's why I can see you. But if your wave function was very weak, stretching, I will not see you. I will see you a distorted person. You can be described actually by physics. So I liked it. Then I did astronomy. After exam, there was a break. So I went to a library, brought a book of astronomy, and I found universe suddenly, which I didn't think of. So vast, so many things are there. And everyone gets fascinated by the vast universe, like you also did.
When I was a boy, I wanted to be an astronomer.
Because it's so vast, and we cannot even, mind-boggling thing, But I had to have reason. Why should I study space, It is not like I'm helping humanity. That is what my parents taught me. So I have to find a way, why should I study? Then I found about meteors and asteroids, they come and hit the Earth. So at age, right after high school, they're coming and they can destroy the whole Earth, and we will be all gone. Dinosaurs, we know that they died because of an asteroid hit, right? Mm-hmm. And when it hit, it created so many dust, and the air circulated and covered the whole Earth. Sun didn't penetrate. Everything was cold. Dinosaurs didn't have food. They died. But they were not studying. If they were studying to protect themselves, maybe they will still be surviving. Even nowadays, we still don't know how to protect ourselves. If an asteroid is coming, we don't know. But ideas are there. So in space, the gravity is very weak. On Earth is very strong because a lot of mass. So if asteroid is coming, if you just, knock it out a little bit.
Nudge it.
Yes. You can just divert the path. But even to do that, slight diversion, we need, say, if you watch Star Trek, what they do when they're going through asteroid, they use laser beam.
Right.
So the laser beam you can deflect. We don't have that laser beam yet.
They say science fiction always seems to have the answer.
But they are useful. Yeah. We use them for ideas. So nowadays, the latest what we did, we sent a probe, and when asteroid is coming, this is the recent, maybe 1 year ago, the probe, it just, we just send the probe and launch and smash on the land so it can deflect it. So, but it takes a long time. It has to reach there and find it. So we need a lot of development to be done.
Mm-hmm. Yeah. What's next for your research?
Okay. Number one is sun. Sun is very important for us because it is
the most important.
Most important, you're right. Without it, we cannot survive. It's the source of energy for us. But it is also the standard to study astronomical objects. Mm-hmm. So we have to know the sun very accurately, study it all the time and know what is happening, what it is made of, what is the physical condition, what is the chemical evolution going on, all kinds of information. So to do that, we have to study also the light coming through. There is a fundamental quantity called opacity. Like opaque, the light cannot go through it. How much light is being absorbed by the materials of the sun, which is largely plasma, ingredients or elements absorbed. That quantity is used to calculate many things. It's a fundamental quantity. So we are aiming to get an accurate opacity. To do that, we have to study the radiation passing through it and how they are being absorbed by the elements. But past study, they they did not do the precise study of the atomic species. Supercomputers are not there. That is one thing. And so it was difficult. Theory was not completely developed. But now we have those in hand. But it is not easy. See, I've been working on iron ions for a long time. And each one takes so much time. It uses so much resources of Ohio Supercomputer Center. After it completed, it takes a long time to complete. But it is important, particularly iron. Okay, why iron? Sun has a lot of iron, and it can be excited in many ways. It can deal with radiation more than other elements. So we study iron in a particular area and try to find out, how they are being absorbed very accurately, so that I can calculate very accurate parameters. Those can be used to calculate very accurate opacity, and that can be used to get other information. Like another is stars. We see. If we see, we always have to use the standards of the sun to predict, what's the condition. But if sun, there's something wrong, uncertainty, that uncertainty will creep to study of the other stars. So we want to make very accurate study of the sun. So that is what I'm doing. So I've been studying sun for a long time, particularly elements inside, particularly iron, and how radiation is interacting with iron ions. So we have a grant from National Science Foundation to do this study. So we're working on that. So this is high priority. I have also exoplanet, this phosphorus, and also the other one, kilonovae, that was very important. Kilonovae means a merger of two black holes or two neutron stars. Neutron stars, you can say, is about almost the black hole. It was short of little bit mass. Okay, black hole needs a lot of mass to become black hole, but if it's a little bit short of mass, it can become neutron star. So it is almost like black hole. So when they merge, we call it, kilonova event, okay, for example, merger. So when they merge, something happens, it creates strong, detectable gravitational waves. We know they have waves, right? I said I can describe you by a wave function like that. So gravitational wave was predicted long time, but it was not detected. Many effort went to detect it. It must exist, but we are not able to detect it because it is too weak to detect. So the Russians have some idea, use laser spectroscopy. The laser, they will do spectroscopy and detect it. Then this idea was picked up by American astronomers, and they said, okay, let's build and set up so we can create a laser spectroscopy which can detect tiny variation in the Earth. If the gravitational wave is passing through us, at the same time when it is passing, both of us will be stretched a little bit and contract back. But it will be very small. So it is not detectable. The idea was how to detect it. The LIGO setup, they created. There's a laser. Laser goes, there are two arms, one this way, the other at right angle, this way. So same distance. A laser goes there and comes back. The same laser, but with a mirror we can split it into two parts. One goes this way, one other goes that way. So when come back is the same, at the same phase they are coming back. But what will happen if the Earth stretches due to gravitational wave? One side will be stretched longer than the other side, right? So when they meet, it will not be exactly the same phase. There will be tiny difference. That's the signal. That's how we detected gravitational waves.
Sultana Nahar, thank you.
You're welcome.
Voices of Excellence is produced and recorded at The Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Voices of Excellence is produced by Doug Dangler. I'm Jen Farmer.